Special course in mathematics, lecture 5, combinatorics. We start with the pigeonhole principle. So recall that the pigeonhole principle is usually formulated in the following way. If n items are put into m containers and the number of items is strictly bigger than the number of containers, then at least one container must contain more than one item. This principle is also known as Dirichlet box principle or Dirichlet drawer principle. Here are some alternative formulations. If S and T are finite sets and the cardinality of S is strictly greater than the cardinality of T, then there is no injective function from S to T. Dually, if S and T are finite sets and the cardinality of S is strictly smaller than the cardinality of T, then there is no surjective function from S to T. And the general remark is that this can be generalized to infinite sets using cardinal numbers. Here is an example of how a pigeonhole principle can be applied. Choose n plus 1 different numbers among the numbers 1, 2, 3 and so on up to 2n. Prove that there is one of these chosen numbers which is a multiple of some other chosen number. Proof. We start by remarking that each positive integer can be uniquely written in the form 2 to the power n times b for some odd b and some non-negative integer n. And for integers between 1 and 2n, the possibilities of values for b are 1, 3, 5 and so on, all the way up to 2n minus 1. And these are exactly n possible values, and these will be our pigeonholes, our boxes. The n plus 1 numbers which we choose are our pigeons or our items. So we have n plus 1 items and we have n boxes in total. So there is at least one box which contains at least two of the chosen numbers. So these two chosen numbers, then they should have the form, one of them is 2 to the power n times b and the other one is 2 to the power m times b, where n and m are two different numbers and we can say that n is smaller than m. But in this way, of course, 2 to the power m times b is a multiple of 2 to the power n times b. And this completes the proof of our problem. Before formulating the main problem, which we will look at today, we have to talk about increasing and decreasing subsequences. Let a1, a2 and so on ak be a sequence of different integers. We will work with integers today. Definition: a subsequence ai1, ai2 and so on aim, where i1 is greater than or equal to 1 and then i2 is strictly greater than i1 and so on. Im is the biggest one among these indices and it is less than or equal to k. So this subsequence is increasing provided that a sub i1 is strictly smaller than a sub i2 and so on. And similarly, this sequence is decreasing if a sub i1 is strictly greater than a sub i2 and a sub i2 is strictly greater than a sub i3 and so on. For example, if we take as the original sequence the sequence 4, 2, 5, 3, 1, 7, 6, then in this sequence we have an increasing subsequence 2, 3 and 7. So 2, 3 and 7 is an increasing subsequence of the original sequence. And similarly, the subsequence 4, 2, 1 is a decreasing subsequence in our original sequence. So today we will look at increasing and decreasing subsequences, and here is our main problem. Let m and k be two positive integers. Let a1, a2 and so on a sub mk plus 1 be a sequence of different integers. Claim: this sequence either contains an increasing subsequence of length m plus 1 or a decreasing subsequence of lengths k plus 1. And our first proof of this claim will be using the pigeonhole principle. To prove the claim, let us assume that there is no increasing subsequence of lengths m plus 1. Therefore, this means that the longest increasing subsequence has lengths m or smaller. So for each I between 1 and mk plus 1, let ci be the lengths of the longest increasing subsequence, which starts at a sub I. So these lengths, they will be our boxes. So by assumption, we have at most m boxes, so our lengths are the values between 1 and m. So we have m boxes, and we have mk plus 1 pigeons. So our i's between 1 and mk plus 1 are our pigeons. So by the pigeonhole principle, we have m boxes and mk plus 1 items, so there should be a box with at least k plus 1 items or pigeons. So let these k plus 1 pigeons be the values a I1, a I2, and so on, a I sub k plus 1, where I1 is smaller than I2, and so on, smaller than ik plus 1. But then this sequence, this is a subsequence of our original sequence. This subsequence should be decreasing because of the maximality assumption. If two elements in this subsequence are not decreasing, then they are increasing because we talk about the same integers. But then the lengths of the longest subsequence in the starting one should be one greater than the length of the longest subsequence in the second one. But they coincide because of the maximality assumption. The corresponding ci's cannot be the same, but these two numbers belong to the same box. And so we get our contradiction. So this contradiction proves our claim. And the rest of the lecture is devoted to a completely different proof of this claim, which uses much more advanced combinatorial approach. So, and this approach is based on what is known as the Robinson-Shenstedt correspondence or Shenstedt's insertion algorithm. And in order to define it, we first need to talk about partitions and Young diagrams. So let k be an integer. Definition: a vector lambda consisting of lambda 1, lambda 2, and so on, lambda n, of positive integers is called a partition of k if it is weakly decreasing, so lambda 1 is greater than or equal to lambda 2 and so on, and the sum of all lambdas is equal to k. And this is the usual notation: lambda is a partition of k. So for example, for the integer k which is equal to 4, we have the following partitions of 4. 4, then 3, 1, 2, 2, 2, 1, 1, and 1, 1, 1, 1. So we have in total 5 different partitions of 4. And if we have a partition lambda of some k, then the Young diagram of lambda is a finite collection of boxes or cells which are arranged in a left justified rows, and row I has exactly lambda I boxes. So for example, the Young diagram for the partition 4, 3, 2, 2 is here. So we have 4 boxes in the first row, 3 boxes in the second row, and 2 boxes in rows 3 and 4, and it's a left justified. On the left, all boxes, starting boxes, are aligned. So that's a Young diagram of a partition. Now, Young diagrams can be filled in with integers to obtain Young tableaus. So a Young tableau of shape lambda, and this shape should be a partition of some integer k, is obtained from a Young diagram of this shape by filling the boxes of this Young diagram with different numbers from the set 1, 2, and so on up to k. Each box should get one number. And the generalized Young tableau is a similar thing, but the numbers which we fill in the generalized Young tableau can be arbitrary, not necessarily between 1 and k. So for example, here are some Young tableaus of shape 4, 3, 2, 2. So the first one, we fill in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, left to right, top to bottom. Or we fill them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, top to bottom, and then left to right. Or we just fill in them in some order, so 1, 11, 2, 7, 8, 6, 5, 4, 9, 3, 10. A generalized Young tableau is called standard, provided that all its rows increase left to right and all its columns increase top to bottom. And the set of integers which are filled in a Young tableau or in a generalized Young tableau is usually called the content. So the content of a Young tableau is always a set of all integers between 1 and the size of the tableau, the number of boxes. For generalized Young tableau, it's arbitrary. And in our example, we had here 3 Young tableaus of shape 4, 3, 2, 2. The first two are standard. Rows increase left to right, columns increase top to bottom. And the third one is not standard, because, for example, 11 is before 2, so the first row doesn't increase left to right. So there are standard Young tableaus and not standard Young tableaus. Now we will discuss an algorithm of how to insert a number in a row. The input of this algorithm is a sequence of integers a1, a2, and so on, ak, and an additional integer b. So where k is some non-negative integer, all integers b, a1, a2, and so on, ak are from 1, 2, 3, and so on, and they all are different. So a1 is smaller than a2, is smaller than, and so on, is smaller than ak. So the starting sequence a1, a2, and so on, ak is increasing. And b is different from any of these ai's. So all the integers involved in this algorithm must be different. And in order to formulate the algorithm, we have to consider two possible cases. Case 1, if b is greater than ak, then we simply add b to the sequence as the last number and also give the full stop sign. So after this, everything terminates. Case 2, if b is smaller than ak, then we find the minimal s, the minimal of all the indices I, for which b is smaller than ai. So in this sequence a1, a2, and so on, ak, it's increasing. b is definitely smaller than ak by assumption, so there exists the minimal index s, such that the corresponding as is still bigger than b, but as minus 1 is smaller than b. And in this case, the output is as follows. The element b replaces as in our sequence, and as is bumped from our sequence and becomes an extra integer, and it will go in the next step of a different algorithm. So that's a bumping algorithm. If our b is not greater than all elements in our sequence, it bumps the smallest element which is greater than it from the sequence, and that element is carried over to the next step of the algorithm, which will be discussed on the next slide. Okay, so before we discuss that algorithm, some examples. Example 1, if we insert 2 in an empty row, then we get a sequence 2 and full stop. Example 2, if we insert 9 in the row 2, 4, 6, 8, 9 is greater than 8, so we write 9 next to 8, we get 2, 4, 6, 8, 9, and full stop. And both these examples correspond to case 1 of the previous algorithm. So in this case, the output row will be one box longer than the input row. Example 3, if we insert 5 into 2, 4, 6, 8, then we know that 5 is smaller than 8, and then we find the smallest element in our row, which is still greater than 5, and that's 6. So 5 bumps 6 out of the row, We get a new row 2, 4, 5, 8, and 6 is bumped. That's a new element which is carried over to the next step. So 6 is the smallest number in the input row that is greater than 5. And this is how the case 2 of the algorithm works. We get a new row of the same length, but it is modified. The number bumps something from that row, and there is a new number which is carried over to the next step. And note that here there is no stop signal, so the algorithm will go further. The next algorithm will go to the next step. Let's explain it, and that's an algorithm how to insert a number in a tableau. So the input of this algorithm is a standard generalized Young tableau of some partition shape. So this means that the shape is a partition of some non-negative integer. Each box in T is filled with some positive integer. All rows of T increase left to right, and all columns of T increase top to bottom. And then we also have a positive integer b, which does not appear anywhere in the tableau T. That's a new integer. And the input of this insertion algorithm is a pair of such T and b, and the output will be a new standard generalized Young tableau of some shape, and that shape is obtained from the shape of T by inserting a node somewhere such that the new shape is again a Young tableau. That's usually called an insertable node. And the content of the output will be the content of T plus the new integer b. So let us describe the algorithm. It's called Shensted's insertion algorithm. So our input is T and b as on the previous slide, and the algorithm goes as follows. We insert b in the first from the top row of T. If the outcome gives a stop sign, everything terminates. If not, the first row of T is changed, something is bumped, and we have a new integer, let's call it C. And now we take C and insert it in the second from the top row of T. And again, we either get a stop sign, and then everything terminates, or the second row is changed, it gives a new number D, and we try to insert it in the third row. And we continue in this way until we reach the stop sign. Of course, this terminates after finitely many steps, because T has finitely many rows. In the worst case scenario, we will be inserting a number in an empty row, which always terminates after the first step. So output will be a new tableau R with the following changes relative to T. So assume that the algorithm terminated after changing row number k. So all rows below k in R are exactly the same as the corresponding rows in T. Row k in R differs from the row k in T by an additional rightmost box with some number. And each row above row k in R differs from the corresponding row of T. It has the same size, but exactly one entry is different, because there was a bumping for that row at some step of the Shensted algorithm. So that's what is going on. Here is an example. Let us insert the number 4 into the following generalized standard Young tableau of shape 3 to 1. So we have 1, 5, 6, 2, 7, and 3. We start by trying to insert 4 into the first row. 4 is not greater than 6, so there will be some bumping. And the smallest number in the first row, which is greater than 4, is 5. So 4 will bump 5 from the first row, and the first outcome will be 1, 4, 6, 2, 7, 3, and 5 is bumped. And now we need to insert 5 into the second row, 2, 7. Again, 5 is not greater than 7, but 7 is the smallest integer in this row, which is greater than 5. So 5 will bump 7, and we get a tableau 1, 4, 6, then 2, 5, 3, and 7 is bumped. And now we need to insert 7 in the third row. The third row only has 3, and 7 is greater than 3. So in the third row, we just add 7 as the last new box. So the outcome will be the tableau 1, 4, 6, 2, 5, 3, 7. And as you see, it's again a generalized Young tableau, now of shape 3, 2, 2. Justification: we claim that the outcome of the above algorithm is a standard generalized Young tableau. Proof: all rows increase left to right by construction. If you look at the bumping algorithm for the row, we start from an increasing row and we either add a biggest element at the end, still increasing, or we replace something in the row, but it's still increasing. So the bumping algorithm works well with rows. So we need to prove that all columns in the outcome will also increase and that the outcome is a partition shape. And both these claims follow from the observation that in the next row the change happens weakly to the left of any change done in some row k at the k step of the algorithm. And this property is a consequence of the assumption that the original tableau was standard. So if A bumps some element B, producing a column where A is on top of C, then originally there was B here instead of A, and because of the fact that the tableau was standard, B is smaller than C. And if we place A is smaller than B, so A will be smaller than C due to our assumptions and the definition of the algorithm. Therefore, in the next step, B will have also to bump either C, that's the same element in the same column, or something to the left of it. And this gives us a justification why the outcome is always a standard generalized Young tableau of some partition shape. Now let us define the insertion tableau for some permutation. Consider some element in Sn, so some permutation of integers 1 to 3 and so on, n. Let's call it sigma, and assume that sigma sends 1 to a1, 2 to a2, 3 to a3, and so on. N is sent to an. So define the tableau P0 of sigma as the empty tableau. And now recursively, for I between 1 and n, define the tableau Pi of sigma as follows. The tableau Pi of sigma is obtained from the tableau Pi minus 1 of sigma by inserting the number ai. Definition: the tableau P of sigma, which is the last tableau in this sequence, so that's Pn of sigma, is called the insertion tableau for the permutation sigma. And from our algorithm, we see that P of sigma is a standard Young tableau whose shape is a partition of n. And more generally, each Pi of sigma is a standard generalized Young tableau whose shape is a partition of I. Here is an example. Let's take the permutation 3, 1, 5, 2, 4. That's an element of S5. Then P0 of sigma is empty. P1 of sigma is obtained by inserting 3 into the empty tableau, so we just get 3. P2 of sigma is obtained by inserting 1 into 3. If we insert 1 into 3, 1 bumps 3, so 3 goes to the second row. And we get the tableau of shape 1, 1 with 1 on top and 3 in the bottom. Next we insert 5. 5 is greater than 1, so it goes into the first row, and we get the tableau with 1, 5 in row 1 and 3 in row 2. Next we insert 2. 2 bumps 5 from the first row, and 5 goes after 3 into the second row. So we have a tableau 1, 2 in the first row and 3, 5 in the second row. And finally we insert 4. 4 is greater than 2, so we just add it into the first row. So for the element sigma, which is 3, 1, 5, 2, 4, permutation of 5 elements, the corresponding insertion tableau is the tableau of the partition shape 3, 2, which has 1, 2, and 4 in the first row, and 3 and 5 in the second row. Now we can come back to increasing and decreasing subsequences. So, to each element sigma in the symmetric group Sn, Shenstedt's algorithm associates an insertion tableau P of sigma. Here is a theorem which is due to Shenstedt. Let sigma be an element in Sn. Claim 1. The length of a longest increasing subsequence for sigma equals the length of the top row in the tableau P of sigma. Claim 2. The length of a longest decreasing subsequence for sigma equals the height of the leftmost column in P of sigma. So this statement is not very easy. The proof is several pages and one should be careful with combinatorics. So for the proof, one can look at the original paper by Shenstedt, which is called Longest Increasing and Decreasing Subsequences, and which appeared in Canadian Journal of Mathematics in 1961. And more details about the context, how this is important, in particular for the representation theory of the symmetric group. About this one can learn in the course Representation Theory of Finite Groups, which is available on this channel. Let us look at one example. For our permutations 3, 1, 5 to 4 in S5, we computed that the insertion tableau is of the shape 3, 2, and it has 1 to 4 in the top row and 3, 5 in the bottom row. Note that 1, 2, 4 is an increasing subsequence for sigma. So 1, 2, 4 is an increasing subsequence, and there is no increasing subsequence for sigma of length 4. So 3, which is the length of the first row, is the length of a longest increasing subsequence. Further, 5, 2 or 3, 1, so we have various decreasing subsequences for sigma of length 2, and there is no decreasing subsequence for sigma of length 3. So the height of the first column is the longest length of a decreasing subsequence for sigma. So that's an example. And now we can go back to our main claim. So if m and k are two positive integers, and a1, a2, and so on, a mk plus 1, a sequence of different integers, then the sequence either contains an increasing subsequence of length m plus 1 or a decreasing subsequence of length k plus 1. Proof. Of course, since the only information which is important for this problem is which elements of the sequence are greater than other elements, we may assume that our sequence is an element in the symmetric group S mk plus 1. So let's call this element sigma. Consider the insertion tableau P of sigma. It is a standard Young tableau of some shape. This shape is lambda, it's a partition of mk plus 1. So lambda, this partition, has rows lambda 1, lambda 2, and so on, lambda n. So these are the lengths of the rows. If there is no increasing subsequence of lengths m plus 1, then by Shenstedt's theorem, lambda 1 is at most m. If there is no decreasing subsequence of length m plus 1, then by Shenstedt's theorem, the number of rows, n, is at most k. But lambda is a partition, so each row has length at most m, and there are at most k rows. So lambda has at most mk boxes. But that contradicts the fact that this is a partition of mk plus 1. And this contradiction proves our claim. Here are some extra problems and questions. Problem question 1. Formulate the pigeonhole principle for infinite sets. Problem question 2. Insert 5 into the row 2, 4, 6, 8, 9. Problem question 3. Insertion of some element x in some increasing row resulted in the outcome the row 2, 4, 6, 8, and 9, and the bumped element 7. Determine both x and the original row. Problem question 4. Compute the insertion tableau for the permutation sigma in S7, which looks as follows: 6, 2, 7, 3, 4, 1, 5. And problem question 5. Determine all elements in S5 for which the insertion tableau is the following tableau of shape 3, 1, 1. It has 1, 3, 5 in the first row, 2 in the second row, and 4 in the third row. Thank you very much, and see you next time.